Good evening, everyone. You are in the right place. As you are all entering the webinar here, we are going to be using the Q&A box tonight. So I'm going to give it a few moments for everybody else to continue joining us. But just note that if you have questions along the evening, please use the Q&A box. We will be using the chat box tonight to send you guys links. But for you guys to talk to us, please use the Q&A box. Okay, great. Okay, so we have some cool stuff happening tonight. But before we go any further, as people are still coming into the room, I want to acknowledge that the museum, here at the museum, we are aiming to advance our collective understanding of both Earth and sky. And I'd like to acknowledge the Bell Museum sits on the traditional and treaty land of the Dakota people. I'd also like to acknowledge the Ojibwe people, traditional keepers of the lands to our north. Dakota and Ojibwe knowledge systems are crucial ways for knowing this place now called Minnesota. And we at the Bell honor that knowledge, the values embedded in it, and the people who keep it. Now, questions are my favorite part of the night. So please do use that Q&A box feature in Zoom to send in your questions and comments throughout the evening. We'll be answering as many of those questions live as we can, but we also have some staff behind the scenes to type out answers for when questions come in way faster than we can answer them live here tonight. So keep them coming in. They're my favorite part of the evening. We want to know what you guys are curious about. This event is live captioned. So if you find those captions distracting or not useful, you can hide them by clicking the live CC button on your screen. It should be down at the bottom there. Okay, so tonight is our April star party. If you looked outside, we're actually okay in skies at the moment. It was pretty blue sky, at least out this evening. We might get a few clouds rolling in, but we're going to do our best to see some really cool stuff in our sky tonight. But for starters, how do we even know where we're looking? Well, that's where we get our star map out. You can download this from the Bell Museum's website. You can see here, bellmuseum.umn.edu/starmap. But we'll also put it in the chat that we can just follow that link straight to it here. Now, we're in April, and April skies are a little bit different than March skies because as the Earth continues to orbit the sun, we see different constellations throughout the year. And you may be looking at our star map here saying, hey, how do we even get started reading this? Well, first of all, our map here is a circle because if you were to stand in one spot and look out towards your horizon and look all the way around you, you would trace out a circle. So the outer edge of our map here is actually our horizon. That means the center of this circle on our map here is the point directly above us. It's called the zenith. And so the closer something is to the center of this map, the higher in the sky, more closer to the straight above you it is. Now we have a crescent moon out tonight, which will be one of the first things you can see. You could see it out during the nice blue sky even this afternoon. But one of the other notable things to see this evening is the planet Mars. If we look at our star map here over in the west, we see Mars kind of earlier, kind of towards the beginning of March, was over here closer to the west in the constellation of Taurus. But because the Earth is constantly moving around the sun, and so is Mars, Mars has actually moved across our sky, and here in April, it's closer and actually in the constellation of Gemini. You'll notice it looks kind of like a star, and it might have this reddish-orange tint to it, and it's really not going to twinkle like the other stars do. That's how you can tell you're looking at a planet. Now, there's a lot of other cool stuff out tonight. You can see some constellations. Maybe closer to the center of the map here, you can see Ursa Major, the Big Bear. But you see a lot of these other blue squares on our map, and those are some deep sky objects. So nebulas and galaxies and star clusters. And tonight we have a really cool guest speaker with us here. So Laura Salo from the University of Minnesota's Institute for Astrophysics is here to talk all about galaxies with us tonight. So without further ado, I'm going to turn it over to Laura. Laura, welcome. Thank you for joining us tonight.
I'm so glad to be here. So I have a presentation to show you all on galaxies, and I'm going to pull it up here. Okay, so we have a lot to talk about with galaxies. Galaxies galore. There are a lot of galaxies out there. But to start with, let's just make sure we all know what a galaxy is. I'm guessing that many of you do, and maybe some of you don't. So let's go through that really quickly. You might be familiar with this sort of an image over here on the left. This is our solar system. This is Earth over here. This is the sun, Jupiter, Saturn. And so all of our planets in our solar system orbit the sun. You're probably used to that. You probably have heard that before. And this solar system is actually part of a larger body of stars. And that larger body of stars might look something like this. This is called the Milky Way galaxy. And this entire solar system is going to be, well, I don't know exactly where in here, but let's just say it's, maybe right about there. That's a good enough guess for now. And the sun is just one of those tiny little pinpoints of light. And all of our planets are orbiting the sun. And every single one of these tiny little pinpoints of light in this object over here is a star. And all of this together makes up a galaxy. So this is our Milky Way galaxy. You'll notice these bright blue features over here. We're going to get to those. You already might know what they are, but if you don't, we're going to talk about them later on. So that's the Milky Way galaxy. Now, you probably have seen this before. Maybe you have gone outside at night where the skies are dark and you've looked up, and you may have seen a milky streak of a bunch of stars running across the sky. This line here, this is what I'm talking about. That's the Milky Way. That's the plane of our galaxy, and you're looking at it from Earth. And it's kind of cool that you actually can see it, which you would kind of expect because we're right there in the middle of it. But it's still cool nonetheless. And if you've never seen this, I encourage you, go somewhere far away from a city, out in the country somewhere, when it's dark, and look up and see the Milky Way. It's really cool to see. And it'll look something like that. It looks a little different from where you are and all that, but something along those lines. So a galaxy, we can give it an actual definition. The definition's a little, well, nebulous. Some people like to change it a little bit. Anyway, the working definition that we're going to use for tonight is a gravitationally bound system of stars, gas, dust, and dark matter. So a system that's kind of all stuck together, held together by gravity, and we've got stars in there, we've got a lot of gas in there, we've got dust in there. Yes, there is dust out in the universe. And we got a lot of dark matter in there too. So that's the galaxy. Now, this is really cool. This is just a fun fact. But the word galaxy actually comes from the Greek word gala, meaning milk. And so the ancient Greek astronomers looked up at the night sky and they saw this milky band across it. And they saw the Milky Band, and gala is the Greek word for milk, and that became the Milky Way as we know it today. So that's how the term galaxy was originated. So just a fun fact. Okay, so we know we are in a galaxy, the Milky Way. There is at least one galaxy out there, but how many are there? Well, there's a lot more than one. So maybe you've heard of the Hubble telescope. Maybe you haven't. It's a telescope that is orbiting the Earth. It's not here on the Earth, it's orbiting the Earth. And it's a really cool telescope. I really like it. And so some astronomers took the Hubble telescope once and they pointed it towards a dark place in the sky, a place where they didn't see a whole lot. And they just let it sit there collecting light to see what it could see. And this is the image they got. It sat there for a long time, so a long exposure, but this is the image they got. And there are a few stars in this image. Like this is a star over here. You can kind of see the diffraction pattern there. That means it's a star. This is a star down here. There are a few other stars, like this one might be a star. This one way up here might be a star. But most of these things that you see in here, these are all galaxies. And yeah, so the orange ones, there's an orange one up there. Well, I guess you technically call it red, but they look orange to me. And you've got some blue ones and even some like green dots in there. Those are all galaxies. There are a lot of galaxies. So just to give you some numbers, there are, you can say about 100 billion stars in a galaxy, and there are about 100 billion galaxies in the observable universe. Different people will give you different numbers. We don't know exact numbers, but that's a rough estimate. So a lot of galaxies and a lot of stars. So that's how many galaxies there are. Now we're going to talk about ways to categorize these galaxies because we know what a galaxy is now. So can we put them into different groups? And we're going to talk about 3 ways tonight. We're going to talk about galaxies' shape, size, and color. So we're going to start with shape. All right, so we're looking over here in the top left-hand corner. These are elliptical galaxies, and they kind of look like ovals. Galaxies tend to be thin disks, so think like a pancake or a frisbee or something. And these are, well, elliptical. They're ovals. They're called elliptical galaxies. And they're pretty uniform. They look kind of boring. They're not. They're very interesting, but they kind of look a little boring. That's okay. Over here, we have spiral galaxies. And, well, the name fits them very well. They go in a spiral. And we've got spiral arms. You can kind of count them in here. I was trying to guess. I was saying maybe 3 spiral arms there. I don't know, maybe you could make out 4, maybe they're kind of not very well distinguished, but there are spiral arms there, you can tell that much at least. This one, it's a little bit easier. I was going to say that there are 2. You might even convince me that there are 3 spiral arms there, but spiral arms. And then this one, those are really hard to count, the spiral arms there. This spiral galaxy is a little bit special. It's called a flocculent spiral galaxy. So we've got, that just means that you can't really see where one arm begins and the other one ends and things like that. And it's just, it's a spiral, but you don't see the arms. Okay, so we have ellipticals and we have spirals. And then we have a category for everything else. And this is called irregulars. And they look really fun, don't they? I mean, this one kind of looks like a question mark almost backwards, but I think they're fun. But they're not ellipticals and they're not spirals. And so why do you think there are these irregular ones? Why don't we just have ellipticals and spirals? Why isn't that just it? Well, galaxies kind of float around out in space, right? And there's this thing called gravity that pulls things together. And so eventually, over time, galaxies are going to merge. They're going to come together, they're going to interact, and then you're going to get 2 galaxies that form a larger single galaxy. And so one good explanation of what these irregular galaxies are merging galaxies. If you have 2 galaxies coming together, they're going to kind of disrupt the normal shape of the galaxy, and things are going to get twisted around and all of that and make some pretty cool shapes, but not elliptical and not spiral. And so they're called irregular. There might be other reasons, but yes. Yes, Sarah?
Sorry, we had some questions coming in
Cool.
about our galaxies here and what we see in these pictures. A few people are wondering, does every galaxy organize around a sun? Because it looks like there's some pretty bright stars in the center of these. Is that bright area one star, a sun? Or what is that bright thing that they're all organized around?
That is a very, very good question. That thing in the center is called the bulge. So every single little pinpoint of light in here is a star, and our sun is also a star. So our sun, it's very big, right? I mean, it's huge compared to us, but compared to the galaxy, it's tiny, very tiny. And so what this is here in the center is a whole bunch of stars, a lot of very bright stars in a very small area. So it's pretty dense in there with a lot of stars. And that's why it's glowing so brightly. We've got some images later on that explicitly show us what the bulge looks like. We've got, you know what? Why don't I just flip ahead and see if I can find it really quickly? Because there we are. Oh, not that one. Not that one. There we go. Here it is. This right here, this is the bulge. And so that's a bunch of stars there, but you can see how it's kind of poking out above the disk of the galaxy. This one's edge on. This isn't face on to us. So that's what we're looking at there. And going back to that's where we were. Sarah, did we have another question to answer now?
So as we're talking about, and you'll probably get to this too, but what kind of galaxy is our Milky Way? We have three types in front of us, but which one are we?
And that takes me right to the next slide. Now, can I switch to, there we go, on to the next slide. This is an image of our Milky Way. What do you think? What does it look like? Well, if you think back to the previous slide, it looks like a spiral galaxy. So yes, it's a spiral galaxy. That's a very good question. I'm glad you asked about the Milky Way. It's important for us to know about our home. So yes, this is a spiral galaxy, and that's not the point of this slide though, but I'm glad that it's on the slide so we can talk about it. We've got some other bright blue spots over here, which I told you we would get to, and we're getting to them now because these happen to be small dwarf galaxies that are circling our galaxy, our Milky Way. And this is just another image of a dwarf galaxy just to show you a slightly different one compared to these. These two are called the Magellanic Clouds. We have the Large Magellanic Cloud, which is abbreviated LMC, and the Small Magellanic Cloud, abbreviated SMC. And they are our closest neighbors to the Milky Way. And you can see that they're smaller. That's why they're called dwarf galaxies. And dwarf galaxies are smaller, they have fewer stars, and generally they're also a little bit dimmer. But they have stars, they have gas, they have dust, they have dark matter in them, and they've got some other stuff in there, sure. I'm sure that there, other stuff in there too, but at the very least that much. And so that's the distinction in size that also matters for our classification. Sarah, before I go on, were there more questions related to the shapes?
So one question I think is related to this picture, and then let's hear more what you're working on. But if we're inside the Milky Way galaxy, how can we take this picture of ourselves?
Oh, I'm glad you asked. I meant to mention that. So we have not left our solar system yet. We've sent a probe outside our solar system, but not us personally. So we've definitely not left our galaxy yet. So we can take a bunch of different data and observations of things though. And so this is actually just an artist's rendition of the Milky Way. It's a drawing. It's not actually a picture of our Milky Way. This is not what our Milky Way looks like. That I hope we get someday because that's going to be really cool to see what our Milky Way actually looks like. But what we've done is we've taken a bunch of data and kind of constructed our best guess as to what our home galaxy looks like. Okay, so we're going to go on to our last category here of classification, and that's color. And you can see on the two sides of the screen here, we've got some galaxies that look a little bit redder and some galaxies that look a little bit bluer. And you'll notice also as you look at these that the red galaxies tend to be elliptical and that the blue galaxies tend to be spiral. Is that always the case? Well, there are always, always exceptions, it seems, to every rule. But in general, yes, spiral galaxies are blue and elliptical galaxies are red. You might ask, why is that? Well, it has to do with the stars that are inside the galaxies. You see, spiral galaxies tend to be younger galaxies. And that's because they have not, we know that they're younger because they haven't gone through as many mergers as elliptical galaxies have. You see, if you take two spiral galaxies and you have a merge, then they're gonna they're gonna twist around for a bit and for a very, very long time, according to our time scales. Not so long for their time scales, but galaxies are quite long-lived. So when they finally settle back down into a, shall we call it a normal shape, most likely it's going to be an elliptical. And that's just because, well, that's a much easier a pattern for it to kind of stabilize into than a spiral. Now, if you have two galaxies merge, they might form a spiral, but that would mean that one of them must be substantially smaller than the other. So ellipticals have gone through a lot more mergers, and so they're older. So the spirals are younger, and as it turns out, young stars emit blue light. So these blue stars are the young stars. They're in spiral galaxies. These are young galaxies. The red stars are older stars. They're in elliptical galaxies. Those are the older galaxies. So that's our classification by color. And there is another color of galaxies, the green pea galaxies. This one's really fun because they're not red and they're not blue. Well, I guess technically they can be considered blue galaxies. I think they are to some extent, but they also are their own category. And you can see the pictures of them here. They're a little blurry, but you can tell that they're small and they're green. So the name green pea galaxies kind of fits them very well. And these galaxies started showing up in some data that was put onto Galaxy Zoo. Now, Galaxy Zoo is a platform where citizens, that means anyone, anyone who has access to the internet. So you or the person next to you or me or Sarah or anyone else here, anyone can go on to this platform. It's an online platform. I'm going to show it to you later. And it's called Galaxy Zoo. And you can sort galaxies and classify them. And you do it based on their shape, their color, well, not by color, actually, shape, features in them, their, if they've got a bulge in them, if they've got spiral arms, different things like that. And so these galaxies were discovered by citizen scientists. So people like you guys. And so we're going to introduce you to Galaxy Zoo in just a bit, and I hope you try it out some, because who knows, maybe you'll discover something too. Anyway, the green pea galaxies, they are smaller galaxies. They tend to be oxygen rich, and they have a high star formation rate. If that doesn't mean anything to you, that's fine. They're small and they're green. All right. So we looked at the slide a bit ago, but we're going to just revisit it to make sure we know what the bulge is. This is what it looks like. It's a bright spot in the center. They're in spiral galaxies too. I chose the elliptical ones just because they are in ellipticals too, and I found some good pictures with the bulge in elliptical galaxies. So it's a bright spot in the center where the stars are dense. And you can see in this picture, as I pointed out before, it actually sticks up above the plane of the galaxy. And it also sticks down a bit below, but the angle that this picture is taken doesn't show that. That's fine. And some of them are smaller. This one's pretty small. Some of them are bigger. This one's a bit bigger. And then this is a much smaller galaxy over here. And it also has a bulge in it. So it doesn't really matter what size the galaxy is, it can have a bulge. Sometimes the bulge actually like almost dominates the entire galaxy and is really huge. And sometimes they don't have a bulge. But if they do, that's, it'll look something like this. And we have bars in galaxies too. So this is the other part of the galaxy that we're going to talk about. And the bar is, well, it is what it sounds like and what it looks like. You've got this bar that kind of runs across the center of your galaxy. You've got a bulge in there. And then the spiral arms attach to the bar instead of attaching directly to the bulge. So that's what it looks like. Not all spirals have bars, but some do. And there is some thought that our Milky Way has a bar. Others don't think so. I don't know if we know for sure on that. Maybe someone else knows, but yeah, so it's possible. All right, so I want to talk about some galaxies near us. And we've mentioned the LMC and the SMC, the Magellanic Clouds. These are actually visible from Earth if it's dark enough and if you live in the right part of the world. So I'm not sure you're going to see them from Minnesota. But if you go far enough south, you want to look towards the southern horizon, and you want to look probably like, let's say, October through April, I think is a good time range. So think winter. and they'll kind of poke up there a little bit. And this picture some guy took of the Magellanic Clouds, there they are. This is the large Magellanic Cloud and the small one. There's a meteorite that got in the picture, which is kind of a nice effect. There it is. And yeah, so that's what it could look like if you had dark enough skies. But again, this guy used a long exposure to take this picture, and so they might not quite stand out so much to you with your naked eye, although you can see them under the right conditions. Andromeda is our neighboring galaxy. This galaxy, we do have a picture of it, and there it is. And it is near us, our closest neighbor other than the Magellanic Clouds, and it is visible to the naked eye. Again, you have to look in the right place, right time of year, and its skies have to be dark enough. But the constellation Andromeda is located between Cassiopeia and Pegasus. I think it's Pegasus. And the galaxy Andromeda is right there with the constellation Andromeda. So it's probably just going to look, probably something actually like this picture here with the Magellanic Clouds. It'll be kind of like a fuzzy blob up there. This is, I believe this picture was taken with the Hubble Space Telescope. And so obviously it's a much better image than you'll see with your eyes, but you'll see a little fuzzy blob up there. And if you have a telescope, you'll see it even clearer. And it's pretty cool. And I encourage you to try to find it if you can sometime. Again, dark skies help. So that's a lot about galaxies and what they are. Now I'm gonna kind of switch gears just a little bit here and tell you some interesting things about things inside the galaxies. I just made a list here. I'm only going to talk about one of them, but I made a list of just what's in our galaxies. We know there are stars in them. We've talked about that. We know there are planets in them. How do we know that? Well, we've got planets that orbit our sun. Our sun is a star. We're in a galaxy, and we have seen other planets inside galaxies too, inside our galaxy. And so we know that there are planets in there. There are black holes in galaxies. Every galaxy is centered around a black hole. There's a lot of gas in the galaxies, and there's a lot of dust in there. And then there are these things called supernovae. And I actually do research that involves supernovae, not directly on supernovae, actually on the galaxies that they're in. So kind of fits with our theme tonight. But a supernova, what is it? Well, you might be able to just say it's an exploding star. Well, there's a lot more to it than that. A lot of people will tell you that when a star runs out of fuel, it will implode and then explode, and that's a supernova. The actual mechanism for it to explode actually has more to do with the degeneracy pressure inside rather than the lack of fuel, but don't worry about that. We're just going to say they're exploding stars. So a star explodes, and that means it's kind of near the end of its life. Well, at least the first part of its life. Stars kind of they go through many phases, and you say, oh, well, that star is at the end of its life, and then it turns into something else and still exists. So I guess it's not the end of the life. Anyway, exploding stars, that's what a supernova is. So what does this look like? Well, I think this is the cigar galaxy. And this is the normal image of the galaxy. Kind of looks cool. And there it is. And you could go out and you could take a telescope and you could observe it, and it would probably look something like that right now. Well, so I don't know who this was who did this, but someone took this observation. And then another night, on specifically January 22nd, 2014, they labeled their data. That's good. They saw this other bright splotch in their galaxy. And that is a supernova. It's circled there, that little circle there. So that bright spot, it's an exploding star. They become very, very bright, so bright that they stand out in this galaxy. And that's pretty impressive to think about how bright that has to become to outshine all the other stars that are around it and to become that much brighter than the galaxy itself. This is a transient though, so it only lasts for a while. It'll last, well, it depends on what kind of supernova it is, and we're not going to get into that. But it'll last for days, maybe some weeks, sometimes a month or so. But eventually it will fade, and then the galaxy will go back to looking like it did before. Now just some numbers here. We typically see one supernova per galaxy per century. That's not a rule. That's just a kind of general guide. Sometimes there are 2 supernovas per galaxy per century. Sometimes 3, sometimes 10. That galaxy is a little interesting. It's a pretty cool galaxy to study. But yeah, there was one galaxy that had 10 supernova in it within a century for sure, pretty recently. So, but on average, you're going to only see 1 supernova per galaxy per century. And keep in mind, though, we've got a lot of galaxies in our universe. Remember that picture that we looked at where you could see all of those galaxies. There are a lot of them. And so just in a general scan across the sky, let's assume that you can see, oh, I don't know, out to the edge of the observable universe. And you're going to see supernovas occurring about at a rate of 1 per second across the sky. And that's a lot of supernovas, but there are a lot of galaxies out there. And so if you think about it long enough, it starts to make some sense. But yeah, a lot of things happening out there in our galaxy. Do we see all of them? Well, no, because you kind of have to have a telescope pointed in that direction, and the telescope has to be strong enough to actually pick it up. But they're there, they're happening at a rate something greater than 1 per second, but you can just say 1 per second. And fun fact about our Milky Way, we are expected to have about 2.8 supernovas every century. So that's just a fun fact there. And why do we have so many supernova, you might ask? Why is it not just 1? Well, that has to do with the kinds of supernova. You see, we're just going to go this far into it, and then we're not going to get into all the details. But we've got basically 2 types. Type 1 supernovas have no hydrogen, and type 2 supernovas have hydrogen. That's basically the difference. That's it. And in spiral galaxies, remember the Milky Way is a spiral galaxy, you will find type 2, type 1b and 1c. I know I didn't explain the difference between 1a, 1b, and 1c. Don't worry about it. Just know that there's some difference. And so we've got type 2, type 1b, and 1c are found exclusively in spiral galaxies. You're never going to find them in elliptical galaxies, only in spiral galaxies. Type 1a supernovas, on the other hand, they are found in spiral galaxies. In fact, they're mainly found in spiral galaxies, but they also show up in elliptical galaxies. So if you think about this, you can see that because we're a spiral galaxy, we have a lot more potential, shall we say, to have supernovas. And so the rate of 2.8 per century does not seem so large after taking that into consideration. So yeah. That's just a little bit about supernova and supernova in our galaxy. And
there was a question about a supernova.
Yes, let's take questions. Actually, I will just say this is the end of what I have to show you all. And so I will take questions, and then we're going to go very quickly and check out Galaxy Zoo. And we're also going to get to telescope time, I think. So the question on the supernovas.
Yes. So when will our sun go supernova?
A good question. Not in your lifetime. And it will eventually. Let's see. I'm not coming up with a good guess on a number of years right now. Sarah, perhaps you have a good guess. You've probably been asked that question once or twice before.
Well, not all stars go supernova, correct?
That is true. It takes a special kind of star to go supernova, or special conditions. And anyway, but
so from what I'm aware of, our sun by itself is not large enough to go supernova. However, like you said, there are many different types, and there's other conditions that maybe one day in the distant future, like 5 billion years from now, maybe a condition might pop up that we could. but I wouldn't expect it to.
Correct me if I'm wrong, but I'm thinking that our sun might turn into a white dwarf. Is
Correct. That is our
Okay.
projected path for our sun.
In which case, then it could become a type 1a supernova, because white dwarfs do explode. And that's the funny part, where it explodes to end its life, and then it becomes a white dwarf and explodes again as a supernova. And so, anyway, that's the life frame of a star is kind of a weird concept. But so it is possible that the sun will go supernova then. But yes, like you said, it's not going to end in a supernova. And at least we don't expect it to. And yeah, and it won't, don't worry, it won't happen tomorrow. It won't happen in your lifetime. This is way long in the future. So do we have a few other questions to answer right now?
Yes, let's answer like 2 more questions here. But as we switch over between this and Galaxy Zoo, let's see if we can take a look at some of our telescope feeds as we're getting ready to switch gears here. Because we are going to look at some of our telescope feeds. Tad and Megan are up on our roof deck right now getting the telescopes ready for us. So if you've been waiting for that, it's coming. We didn't forget about it tonight. But a few more galaxy questions came in. How long would you have to watch a typical spiral galaxy to perceive rotation in the spiral?
Oh, that is a good question. Let's see, I've not set an actual time frame to this. I believe in our Milky Way that since the dinosaurs went extinct, we have gone about a quarter of a rotation around our black hole. So the dinosaurs went extinct a while ago, and we've gone a quarter of the way around. So it depends on how much of a rotation you want to see as to how long you want to look. But yeah, that should give you some sense of time.
So definitely not within our lifetimes then.
Yeah, probably not.
Okay, you talked about irregulars maybe having been the mergers of other galaxies. So when 2 spiral galaxies merge, do both their centers stay or do they merge as well?
Oh, that's a great question. So there's centers. What we're talking about is the very, very center is going to be a black hole at each. And so the centers are, well, you see, first they just kind of pass by each other, but remember, gravity. And so they're going to start to be attracted to each other, and they're going to kind of start to orbit each other and kind of spiral in towards each other. And eventually they will merge. And that is actually a black hole merger. That's something that LIGO observes. I don't know, maybe you've heard of LIGO, gravitational waves and all of that. It's really cool stuff. But yes, the centers will eventually merge. Those black holes will merge. It might not happen immediately, like the galaxy might pretty much settle and finish its merger before they merge, but they will eventually, yes.
Okay, well, let's go over and switch over to Galaxies that you mentioned, because that's a way we can get involved in studying galaxies from home. So Galaxy Zoo is this really cool thing. If you look in the chat box, we did put a link to it in there for you. So if you want to follow along on your home screen, you can, or you can just click on it and save it for later here. But Laura's here is going to help us walk through, like, when we look at galaxies, what are we looking for? Because this is going to be a citizen science project, which means you are just as good at determining what you're looking at as the experts are. Because it turns out we're all human, right? And humans, we can look for patterns in these images. And if enough numbers of people look at the same image, the kind of the consensus rises to the top, and that can help researchers out immensely. So it's called citizen science because you actually get involved in the research itself. And Laura, correct me if I'm wrong, but it's actually the discovery of those green pea galaxies you were talking about that citizen scientists at home discovered using this Galaxy Zoo.
That's correct.
Okay, so what do we do with Galaxy Zoo once we click on the link?
Well, you're going to get a little tutorial that shows up. I'm going to skip that for now, but you can read through it. It kind of explains it. And if you ever forget what you're doing, it's right over here. And you can always just go over there and click on it and get a refresher. They also have this need some help with this task question down here, and that'll give you a few hints too, should you need them. But what you're going to see here is you're going to see a picture of a galaxy. Now, the thing to know is that the galaxy that they're asking you about is going to be in the center of the image. So sometimes there's like a really cool, interesting galaxy down here, but that's not the one they're asking you about. They're asking you about the center one. So we're looking at this one here, and we're just going to step through this, Sarah and I, and you guys can listen along and watch us try to come up with some answers here as to what we think this galaxy is. So Sarah, I'm going to start by saying I don't think this is a star or artifact. I think we actually have a galaxy here. They do have these helpful pictures on the side, and you can just kind of match it to that. So this doesn't look like a star to me.
No, because you showed us the picture earlier that the stars have kind of those crisscrosses in front of them, and I'm not seeing that in this picture.
Yes, I think we can rule that out. Do you think this is smooth, or do you think we see something in there?
Well, I can definitely see that center bulge you were talking about, the bright spot in the center, but it's pretty smooth. I don't really see any defined arms or anything else. It just kind of fades out from there. So I think it's pretty smooth.
Okay. I would have said that there's a feature there because I do see the disk. I mean, not the disk, the bulge. I do see a bulge in there. And so I would have thought that it would be a feature.
So maybe that's something we use a tutorial for, is does the bulge count as a feature? Because I do see that bulge.
And I've gone through this a few times. So yes, it does. They do ask you about the bulge in this one. So it is important to notice that. We could pull up the tutorial if you wanted to see that. Do you want to see that, Sarah?
If you just looked over it, I'll leave that. I'll trust you. And then if you have questions at home, definitely click that tutorial, because I see the bulge. I have no question about it. It is there. It's that bright spot in the middle.
So we're going to say it's a features or disk, and it falls in that category. And let's see what comes next. Okay, so now we're getting the question, is this edge on or are we not edge on? So you remember that edge on picture that I showed you in the presentation where you could actually see the bulge sticking out on top of the galaxy? That's what it looks like edge on. Sarah, I'm thinking we're not edge on. Do you agree?
I would agree with that. It doesn't look long and skinny.
Yeah, okay. Let's go with no, something else. All right. And then it's asking about a bar. And they show us examples of bars here. A bar, it's longer, right? It's long and thin, and it's kind of in the center. Do you see a bar, Sarah?
I am not.
I don't either. So we agree, that's good. No bar. Spiral arms. No. Central bulge, yes. All right. Now we get to choose our size. Well, no bulge, that's ruled out because we have a bulge. What do you think? Small, moderate, large, or dominant?
Well, it's pretty big. So, but it's not dominating the whole thing. So I'm going to say like a moderate or large would be my assessment. What are you thinking?
I'm thinking based on these pictures here and how far out the light goes, I'm going to guess moderate. Does that sound okay to you?
Works for me. Let's go.
All right, moderate. Next. All right, do we see anything interesting here? Well, I mean, there's this other galaxy here, but it doesn't look like they're merging because they're not stretched out. They're not funny shapes. And I'm not sure I see any other disturbances. Do you?
I don't either.
Okay, let's say none. And then any of these features. A ring. I don't see a ring. A lens or an arc. No, I mean, that's kind of a little spread out over there, but I don't think that counts too much. Irregular, no, this is pretty elliptical, I think. Dust lane. Overlapping, something else, nothing unusual. What do you think, Sarah?
I'm not seeing anything unusual here. It doesn't really match any of those pictures.
Okay, I agree. Oh, sorry, clicked the wrong one. There we go, nothing unusual. And done. And then it gives me a new galaxy. And Sarah, do you want to go through this one, or shall we just?
I think that's a pretty good example of how you go through this. Because there's always a tutorial that you can work on at home too. And the great thing is you can see here in the picture says you should sign in because you could keep track of your own classifications. Or you could just do it anonymously like we've been doing here tonight so far. So this is a really cool project, and Galaxies is just one of many citizen science projects you can do at home through this platform here.
Yeah, there are many. You can do them in and everything. They've got like biology, they've got like plant stuff, they've got other astronomy projects. If you really like graphs and things, they've got those too, and all that. I do want to point out one cool feature that it took me a while to notice, but there's this switch to dark theme here, and it makes your entire background dark. And sometimes this really helps you see the image better. And so that's just something to keep in mind. If you're unclear if you're seeing it correctly or not, you can always do that. And this one also, this little half moon thing here, it switches everything from light to dark and dark to light. And so that can also help you distinguish different features and things if you're on the fence and kind of like, well, I don't know if that is, looks like this or that or something. You can always click that. So just a few notes there.
Wonderful. And again, that's Galaxies Zoo. It's one of many citizen science projects. And it's looking like we're just about to go see some galaxies in our own night sky tonight. So tonight was all about galaxies. Laura's talked about them. We'll hang on for a little while more with Laura because we have lots of other galaxy questions.
All right, Laura, can you classify this galaxy?
This galaxy, well, let's see.
It's not a Hubble Space Telescope image, that's for certain. It's
Yeah,
just our roof deck upstairs in the museum.
And we definitely have some star trails there. Sorry about that.
That's all right. Let's see. Well, I'm seeing here that the center is brighter than the edges. So I'm going to say that there's a bulge in it, but I don't see any spiral patterns. So I'm going to call it an elliptical galaxy.
Ooh. So our star trails have messed this one up. I'm sorry to say there are some spiral arms here. There's actually 2 galaxies, believe it or not.
Huh? I guess I can't see it all that clearly.
No,
then.
I'm sorry.
It's not the Hubble, but this is it's kind of cool to see that you can do this from your backyard, or in our case, our observation deck with the camera through our telescope. So again, it's not the Hubble, which maybe you're a little bit more used to, and that we use for Galaxy Zoo. But this is a live shot. Tad, what galaxy are we looking at?
We are actually looking at 2 galaxies known as M51 and M51b.
Okay, now correct me if I'm wrong, that sounds like the Whirlpool galaxy, correct?
That is the Whirlpool galaxy. So I might actually try reshooting this, restarting our stack, because these spirals, they were showing up beautifully as like right before I popped it up. Of course, they were showing up beautifully. So we might try bringing those back here, because this is a beautiful face-on spiral, magnificent star. There's a lot of star formation going on here that really makes it pop. It is just an outstanding galaxy to view. We also have some light haze, which is messing things up. So, we're going to try this one again, just to see if we get a better view here.
Okay, so while Tad is refreshing our live images from upstairs on a roof deck, Laura, there's a few other questions. What would happen if, I'm assuming we were in an elliptical galaxy? I think that's what this question is asking. What would happen if we, here in the solar system, lived in an elliptical galaxy instead of a spiral?
Well, elliptical galaxies, the stars still orbit the center, so we'd still be going around. You would still have a star to orbit. I don't think your star would be like our sun, though, because the stars in the elliptical galaxies are older stars and redder stars. And so it's probably going to be more like, maybe a red giant or something that you're orbiting. So I hope you're far enough away, because if you get too close to those, you'll be inside of them. So that would be a difference. But other than that, you're still going to be traveling around, and yeah. Your night sky is going to look different. You're not going to see quite the Milky Way up there. It's going to look a little different, but you'll still see something up there when you look up.
Okay, and then another question. Why does the galaxy shape influence the type of supernova? Because you were talking about how some are found only in spirals.
So it's more of a coincidence, because the ones that are found in spirals, we don't know this for sure, but we think that the progenitors, that means the stars that formed the supernovas, we think that those are younger stars. That would make sense because spiral galaxies are younger. And so it's kind of a coincidence that they're younger, and so they're in the spiral galaxies. And because the younger stars are exploding in these certain supernova types, we only see them there. Does that make sense?
I think so. There's a nickname out there, and I can't remember if you said it, but ellipticals are sometimes nicknamed red and dead. And so, do you want to explain that nickname and why that would kind of influence the stars that we find in there?
Yes. So red and dead. We said that the red stars tend to be older, but the dead portion comes in because the elliptical galaxies are not undergoing star formation, or at least not at the large rates that the spiral galaxies are. So in spiral galaxies, you have a lot of new stars being born, and that's exciting and great, but you don't have that in the elliptical galaxies. And so they're red and dead. The stars are still living, but again, the nickname, it works. It helps you remember it. It might not be perfect, but it works.
Okay. Well, here's one that I think is stumping a lot of people. How are galaxies formed?
Well, galaxies are formed. It's a coming together of mass of stars and stellar dust and all of that. And honestly, I don't know how much scientists know about this. I'm sure some of them know more than I do, but I don't know a whole lot about that. uh,
From
it
what
makes
I've heard, nobody actually really knows. That's why we have people studying galaxies. That's why the citizen science at Galaxies Near Us is so helpful, because if we know enough about a lot of galaxies, we can start to put that puzzle together. So I don't know that anybody knows how galaxies are really formed, because we don't know if how they started out or how they got there. It's kind of the chicken or the egg. Did the black hole get there first? Did the galaxy or the galaxy get there and the black hole formed? There's still lots we don't know about galaxies.
Right, and it's hard to watch them forming because, well, galaxies have a very, very long lifetime, as in like forever. At least I've never known of one to just like up and disappear. And so we can't, their time scales are so long, you can't just like look out into the universe one night and watch a galaxy form. It'd be great. That would help us a lot, but it doesn't work that way. And so, yeah, it makes it hard to learn about it.
Okay, Tad, you're doing a lot of cool stuff on the screen. When you get a chance, what's going on up there? What equipment are we using? What are you doing? So if you don't have a time right now, let us know in just another minute or so.
No, that's great. So what we're doing is we're live stacking. And by live stacking, the goal is to take a lot of images that all have a little bit of good data, and you keep all that good data and you throw out all the bad data. So it works sometimes for us. Laura, I keep trying to get these spiral arms here for you. There's
I'm starting to see them. They're starting to focus. I've seen them a little bit.
Okay. And if you're just being kind, thank you too. Yeah, so right now we are using, it's a camera called ASI, ASI ZWO from the manufacturer ZWO, and it's a 183 monochrome camera for those out looking for it. And it's set up on a Celestron 9¼ inch Schmidt-Cassegrain SCT telescope up on our observation deck. That's actually one of the extra views I have in my camera view here. I'm not sure, it's pretty dark, so it's not going to come out too well, but we need to be dark to capture these images. And yeah, so that's the long and short of it. ASI 183 on a Celestron. It's a good little setup we have up here.
Yeah, and so the Celestron is actually a common telescope that many amateur astronomers have. So it's not Tad said it's a 9¼ inch in diameter. So it's something that many people could have access to if you're searching for a telescope. So it's nothing too special. Now, if you look through the telescope with your eye, you're not going to quite see this image here that Tad's live stacking for us, because we are stacking all those images. So our technology is doing something a little bit that our eyes can't do. But this is something that you can kind of see a faint hazy thing if you were in a dark part of the cities, or get outside the cities and point your telescope in this direction. This galaxy is over kind of by the Big Dipper, if I'm not mistaken. Now, Laura, we have another question coming in about spiral galaxies.
Oh, if I can just say, if you're looking for this in the sky, it is, if you look for the Big Dipper and you look for the handle, the very last star at the end of the handle is called Alkid. And you look it's like a finger width below the last star at the end of the handle. It's very easy to find in the sky if you have a telescope. If you're just looking for the general area as well. Very easy to find.
Good to know. Thank you. So Laura, I'm going to kind of combine two questions. There's one about why do some spiral galaxies spin one way and then others spin the opposite way? And does that have to do anything with the rotation of a black hole at the center of galaxies? Do you know anything about that?
So the spinning of the spiral galaxies themselves, keep in mind that the universe is, well, there's no up or down or right or left in the universe. Well, I guess you could kind of have a right and left in the universe, but there's no like up and down. We have a sense of up and down simply because we have gravity pulling on us. But if you were to move away from the Earth out somewhere else, up and down wouldn't mean much of anything to you. So these galaxies, if they're spinning one way, and then you flip them the other way, they're, upside down, they're going to be spinning the other way. So they spin, and there's not necessarily a way to tell which direction they're spinning. From our point of view, we see them spinning a certain direction. But yeah, it's kind of that question of direction in the universe. Is that related to the spin of the black hole in the center of the galaxy? I don't really know, and I don't know if someone knows, maybe. I know that the black holes do spin. I would guess that the gas and dust around the black hole would spin in the same direction that the black hole is spinning. That would make sense to me, but I guess I don't know for sure that that's the case. And so if that's doing that, then it would kind of make sense that the entire galaxy would be spinning in the same direction. But again, I don't necessarily know that that has to be the case. And the galaxy could just be spinning around it from the way that the momentum that it already had. Sarah, do you have any better answers than that?
I don't know if there's any data that shows the spin direction of a black hole relates to the spiral arm direction of a galaxy. Black holes, while they are very massive compared to a galaxy, they're very small in size. So I don't know if there's going to be a correlation between the rotation direction of a black hole and the rotation direction of a galaxy. I just don't have the data to say one way or the other. But that's a great question and something that we're, learning about our galaxies and their relationships to the objects inside them, like black holes. So yeah, great questions. A few other questions came in. Can we see Andromeda Galaxy tonight? Now, on your star map, you might be able to see the Andromeda Galaxy on the far west or northwestern corner of our map. The Andromeda Galaxy is best seen in the fall and the winter. It's setting shortly after the sun right now, so it's pretty low on our northwestern horizon. But there's plenty of other galaxies around the Big Dipper, around Leo the Lion, and definitely rising their east around Virgo the Maiden. There's a whole cluster around Virgo, and it's just, you look in that point of the sky with a telescope, and it's going to be filled with galaxies. So spring is really the time, the season for searching for galaxies as we're looking here into Leo, into Virgo, into Boötes. It's a great time to look if you want to know more about galaxies in our night sky. Now we are nearing the end of our time together. And before I kick it back over to Tad, just briefly to see anything else he has left to show us, I do want to let you all know about what we're doing this summer. Because as the nights, as it gets darker later and later at night, we are not going to be here up in the middle of the night here broadcasting you because you guys probably will all be sleeping. So what we're going to do here this summer is we're going to go from evening observing like we're doing tonight, and we're going to switch over to solar observing. So once a month, starting next month in May, we're going to have live solar observing during the daytime. Now, these events are completely weather dependent because the sun is very active. It can be really active one day and not the next day, or vice versa. We could have a bunch of clouds out. So the dates for these solar observing events are going to be posted on our Facebook page as soon as we know what the weather is going to be happening that week. So watch our Facebook page for these once a month solar observing virtual events here as we switch into longer days here in the summer. So I do want to encourage you all to join us this summer for a different version of virtual star parties here, just looking at our closest star, the sun. And last but not least, before I kick it back over to Tad for any last glimpses through our telescopes, I want to thank you all for joining us tonight. Star parties and the astronomy programs here at the Bell Museum are made possible by Ruth and John Huss and the generosity of donors like you. Gifts of any size have a huge impact on our ability to bring programs like this to you. If you feel like you are able and willing and want to give even the smallest donation, please use this link on the page. We greatly appreciate your support and for joining us here tonight. If there's any last questions, we'll try to get through them. And I'm gonna kick it back over to Tad here for any last quick views through our scope tonight. Thank you all for joining us.
All right, well, we are actually trying to track down a star, or rather, we're trying to track down M87. But while that's happening there, brought it back to good old Luna here, or Selene, our moon. This is actually coming through a slightly different camera. There's another ASI camera and a smaller scope of 102 millimeter refractor. But it gives us a nice view of the moon here. I might actually see if we can make this a little bit larger even. Hide some of those other views there. It's a beautiful, the first crescent moon here is just a beautiful sight. We're a little bit, the camera is a little bit tilted from if you're going outside, if you're walking outside and seeing in the sky. It's not quite like this here, not quite like this bowl shape, but it is always beautiful to look at. We have these beautiful, really nice craters that we can see here. We might zoom in a little bit just to bring in a little bit more detail. We got a little out of focus there as we get in, so we won't try to do too much there. And yeah, so this is a great time of month to view the moon. It's definitely not washed out or anything, so it's not too bright. You're not going to go blind yourself if you try to look at it closely with your own eyes or binoculars. Binoculars are really great for the moon, or a telescope if you have one. We can pick out some of the first Mario we see as the moon comes, as it starts waning or waxing here. We're looking, I believe, if I got this right, at Mare Crisium over here, the nice roundish one here. We're starting to see Serenity and Tranquility as well further along. Yeah, and we're seeing, well, it's a little fuzzy, but I guess I've looked at the moon enough. I think I'm starting to see some central peaks in the center of some of these craters. Craters are incredibly complex. Their formation as objects, as rocks smashed in the moon and carve out these holes cause incredible intricate structures. That combined with the history of the moon, early molten rock, volcanics, basically a entirely molten surface with lava flowing over it, has given it many different areas, and then of course continually reshaped by cratering over the past 4 billion years. It's a beautiful sight. I don't know if you want me to keep talking here, so.
Oh, no, I was trying to find my unmute button. Sorry about that. But yes, I think we say it every month. The moon is one of my favorite things to look at through a telescope or even a pair of binoculars. If you know, birding binoculars, especially during this time right around the first quarter, because you get these great details of the shadows crossing those craters. So we often take the moon for granted, and I highly encourage you not to take it for granted. Go outside and look at it, even through a pair of birding binoculars. You can see wonderful detail this time of month.
Just the answer.
Okay. Well, it looks like we've answered all the questions that came in. Are there any last ones? Okay, yes, we are enjoying the night. We're sticking out here, especially when the weather gets nice. Us amateur hobbyist astronomers, we really like to stay out, even though seeing isn't quite as clear as it is in the winter time. And yes, Luna is another name for the moon. So like our sun is the name of our star. You might also hear it referred to as Sol, S-O-L. That's why we have our system of planets around in the solar system.
Okay.
Yeah.
So yes. Okay. Well, it seems like Tad and Megan on the roof deck are having a great time looking at the moon. No more last minute questions have been coming in. Tad, do you have anything last you want to share with us before we sign off for the evening?
Well, we are, in fact, yeah, we're gonna, yeah, give me a second to switch over to our different view here. So this is just sort of a quick and dirty exposure here. It's just shooting continuously at about 5 second exposure here. We are tracking down M87, which I believe should be about here. In the I should say I'm here. I'm pointing out that doesn't make sense to you all. That's in the upper left, sort of upper left center. The software is focused on a star over there, but a bit to the right of the star that it's focused on is hopefully M87. I'm thinking I'm even seeing another galaxy down lower down there too. I'm gonna try to set up a live stack here just to get a little more information from this, from what our scope is seeing.
Dad, is M87, is that the galaxy where we took the first picture of a black hole?
Exactly. Yeah, exactly. Exactly why I wanted to go to it. We just had the anniversary actually of that picture, just a few days ago. And that was it was so exciting to see that again in my memories. And all the excitement of that image and what it means was just so cool. All right. Hopefully this stack works a bit here. We might see a little bit more as we go along.
Okay.
M87 is an elliptical galaxy. I don't know if it's been mentioned along the way. It's an elliptical galaxy, so we wouldn't be able to see the same spiral structure. There's sort of in our views here, there's just this blob of stars, but it's got something like, I want to say something like 1 trillion stars in it, give or take. If someone wants to count them and correct me, please go ahead. And really, I think the beauty in seeing this is really to share in that amazement of knowing that you're looking at the same galaxy where we now have this first image of the area around a black hole, which I think was incredibly amazing because, we got it. Of course, scientists were able to get this image, but also really what it meant and how they got it. I mean, this collaboration between seven scopes, a dozen scopes. How many scopes are around the world, Sarah? Do you remember?
I don't remember, no.
But a good 7 to a dozen scopes around the world, collecting data over years, terabytes of data that had to be shipped via hard drive. It was too much just to send it over the internet. It was actually delayed because one of these telescopes is the South Pole telescope, and it turns out there's some bad weather occasionally in Antarctica. So getting the data from Antarctica was delayed because of the weather. And then putting this together and really, I think, the scientists were incredibly amazed that they got this image from 87, but also amazed because it fit so incredibly well. It was like perfect match to all the theoretical modeling, all the mathematical modeling of what a black hole should look like. Work by Dr. Kip Thorne in particular. And that's frustrating in some ways because it means that we sort of know what's going on. So that's always kind of annoying because you want to find out what you don't know, of course. But then it's incredibly exciting because it's been a lifetime work for these scientists, for these physicists, trying to model these extreme and insane environments in and around a black hole or around a black hole, and to have, I think, their life work really validated by what they found. I think you could hear that awe and amazement and sheer excitement at that in all the press conferences a few years ago. Yeah, so yeah, anyway, that's why I like looking at M87. It might be a fuzzy blob of stars, but there's so much there to think about when you're just seeing that quote unquote fuzzy blob, as I'm calling it. No offense to M87.
Nope, and we're definitely not going to see that black hole because it did take that global effort to see it. But thank you all for joining us one last time, and thank you for staying on for a little bit later to see this really cool galaxy that's in our spring sky here. We do encourage you to go outside, take a look at the sky with just your eyes. If you have binoculars or a telescope, take advantage of those things. The spring sky has wondrous treasures to behold, and the easiest one is to find the moon, and Mars isn't too far away from it. So thank you for joining us tonight. We hope that you will join us this summer for live solar observing virtually here on our Facebook page this summer as we switch over to observing our closest star, the sun. So have a good weekend, everyone. Thanks for joining us. Laura, thank you so much for joining us and being our guest speaker tonight, talking all about galaxies and how they're different. We've greatly appreciated you. Good night, everyone.
Good night, everyone. Stay safe.